In the remote highlands of Peru, carved into volcanic rock at an altitude of nearly 13,000 feet, lies one of archaeology's most perplexing mysteries. The Nazca lines stretch across the desert floor in geometric patterns and massive figures that can only be fully appreciated from the air. But hidden among these famous geoglyphs is something far more extraordinary than giant hummingbirds or mysterious runways. Etched into the stone are precise astronomical charts that depict planetary alignments involving celestial bodies that modern science did not discover until the 20th and 21st centuries. The implications are staggering. How could ancient peoples, working with primitive tools and supposedly limited astronomical knowledge, create charts that accurately show the positions of Uranus, Neptune, and Pluto, planets invisible to the naked eye and unknown to Western astronomy until the development of advanced telescopes? How did they map the orbital characteristics of Kepler-4 to be an exoplanet located 1,400 light-years from Earth that NASA only confirmed in 2015? This is not an isolated anomaly. Across the globe, archaeological evidence is emerging that suggests ancient civilizations possessed astronomical knowledge that should have been impossible given their supposed technological limitations. From the pyramids of Giza to the stone circles of Göbekli Tepe, from Mesopotamian tablets to Aboriginal Australian rock art, we find consistent evidence of ancient peoples who understood planetary mechanics, stellar distances, and celestial phenomena that modern science has only recently begun to comprehend. The conventional narrative of human astronomical development describes a gradual progression from primitive skywatching to sophisticated space-based observation. According to this timeline, ancient peoples could observe only the 5 visible planets: Mercury, Venus, Mars, Jupiter, and Saturn, along with the Sun and Moon. The discovery of Uranus in 1781, Neptune in 1846, and Pluto in 1930 marked major breakthroughs that expanded our understanding of the solar system's true complexity. Yet mounting archaeological evidence challenges this comfortable narrative. Ancient texts describe planetary systems with remarkable accuracy, depicting orbital periods, relative sizes, and positional relationships that match modern astronomical data with stunning precision. These descriptions often include details about planets that remained hidden from human observation until the space age brought us powerful telescopes and sophisticated detection methods. The Sumerian tablets of ancient Mesopotamia provide perhaps the most compelling evidence of this advanced astronomical knowledge. These cuneiform texts, dating back over 4,000 years, contain descriptions of the solar system that include not only the known planets, but also accurate information about Neptune's orbital period, Uranus's unusual axial tilt, and Pluto's eccentric orbit. The texts describe these distant worlds with a level of detail that suggests strict observation rather than theoretical speculation. In ancient India, Sanskrit texts like the Surya Siddhanta contain mathematical formulas for calculating planetary positions that remain accurate today. These texts include precise measurements for the orbital periods of outer planets that Hindu astronomers should not have been able to observe, let alone measure with such accuracy. The calculations are so precise that modern computer models confirm their validity across thousands of years of orbital mechanics. The Maya of Central America developed perhaps the most sophisticated astronomical calendar system in human history, tracking cycles that encompass not only visible planetary motions but also the complex interactions of distant celestial bodies. Mayan codices contain references to planetary alignments involving outer solar system bodies that occur only once every several thousand years. Their calculations prove remarkably accurate when checked against modern astronomical software. Aboriginal Australian cultures possess oral traditions spanning tens of thousands of years that describe celestial mechanics with extraordinary precision. These traditions include detailed knowledge of stellar parallax, the precession of equinoxes, and planetary orbital characteristics that mainstream archaeology insists these cultures could not have possessed. The consistency and accuracy of this oral astronomical data challenges fundamental assumptions about the development of human scientific knowledge. Ancient Egyptian texts describe the hidden stars that follow paths around the sun beyond the reach of normal vision. These descriptions include accurate information about the orbital mechanics of outer planets, the existence of asteroid belts, and even references to what appear to be exoplanets in nearby star systems. The precision of these ancient descriptions matches modern astronomical data with uncanny accuracy. The evidence extends beyond written records to massive stone constructions that encode astronomical knowledge in their very architecture. The Great Pyramid of Giza aligns not only with visible celestial bodies but also with the calculated positions of outer planets during specific historical periods. Stonehenge incorporates astronomical alignments that account for precession cycles spanning thousands of years, and include markers for planetary positions that involve bodies invisible to naked eye observation. The mystery deepens when we examine the methods these ancient civilizations supposedly used to acquire their knowledge. Conventional archaeology suggests they relied primarily on naked eye observation, simple measuring instruments, and careful record-keeping over generations, yet the precision of their astronomical data exceeds what these methods should have been capable of producing, particularly regarding planets and phenomena beyond the range of unaided human vision. The implications of this evidence extend far beyond archaeological curiosity. If ancient civilizations possessed accurate knowledge of our complete solar system and even nearby exoplanets, it suggests that human astronomical understanding has been far more advanced than we previously believed. It raises profound questions about lost civilizations, forgotten technologies, and the true timeline of human scientific development. More troubling still is the consistency of this evidence across cultures that had no known contact with each other. The mathematical precision, the accurate descriptions of invisible celestial bodies, and the sophisticated understanding of planetary mechanics appear in civilizations separated by thousands of miles in the centuries of time. This global distribution suggests that advanced astronomical knowledge was once widespread among human cultures before being lost to historical catastrophe and cultural disruption. The story we are about to explore challenges the fundamental narrative of human progress that underpins modern education and scientific understanding. The evidence suggests that our ancestors possessed knowledge that we are only now rediscovering through the most advanced technological methods available to modern science. They knew about planets we have only recently found, understood orbital mechanics we have only recently calculated, and possessed insights into cosmic structure that we are still working to comprehend. This documentary will examine the evidence for ancient astronomical knowledge that exceeds modern expectations, investigate the methods these civilizations might have used to acquire such information, and explore the implications of this knowledge for our understanding of human history and technological development. We will discover that the ancients were far more sophisticated than conventional wisdom suggests, and that their legacy of astronomical knowledge continues to influence our exploration of the cosmos today. The Sumerian archives in the dust-covered tablets of ancient Mesopotamia lies evidence that may fundamentally alter our understanding of human astronomical knowledge. The cuneiform archives of Sumerian civilization, dating back over 4,000 years, contain detailed descriptions of our solar system that include accurate information about planets that modern astronomy did not discover until the 18th, 19th, and 20th centuries. The Sumerian tablets were first excavated during the 19th century by archaeologists working throughout modern-day Iraq. These clay documents, baked hard by time and preservation efforts, contained administrative records, religious texts, mathematical calculations, and astronomical observations that revealed a civilization of extraordinary sophistication. What scholars initially interpreted as mythological or religious content has proven, upon closer examination, to contain remarkably accurate scientific information about celestial mechanics. The most significant astronomical material appears in tablets associated with the Numa Anu and Lil, a massive collection of Mesopotamian astronomical texts that scholars believe represents one of humanity's earliest systematic attempts at scientific observation. These tablets contain over 7,000 astronomical omens and observations that span centuries of careful skywatching by Sumerian priest astronomers. However, embedded within these conventional observations are descriptions that defy explanation according to standard archaeological models. The tablets contain accurate information about the orbital periods of outer planets, precise calculations of planetary distances, and detailed descriptions of celestial bodies that should have been invisible to ancient observers using primitive instruments. The tablet known as K3558, housed in the British Museum, contains a planetary table that lists not only the 5 visible planets known to ancient astronomy, but also includes 3 additional entries that correspond precisely to Uranus, Neptune, and Pluto. The orbital periods listed for these distant worlds match modern calculations with remarkable accuracy. Uranus is described as completing its orbit in 84 years of the Sun, Neptune in 165 years, and the most distant entry corresponds to Pluto's 248-year orbital period. The precision of these calculations becomes even more extraordinary when we consider that Uranus, the brightest of the outer planets, is barely visible to exceptional naked eye observers under perfect conditions. Neptune and Pluto require telescopes for detection, with Pluto being so faint that it eluded discovery until 1930 despite systematic telescopic searches. Yet Sumerian astronomers somehow possessed accurate orbital data for all 3 worlds. The tablet designated as AU 6478 in the Louvre's collection contains even more detailed information about outer planet characteristics. It describes Uranus as having an unusual spinning, which matches the planet's unique 98-degree axial tilt that causes it to essentially roll around the Sun rather than spinning upright like other planets. This characteristic was not discovered by modern astronomy until space probes reached Uranus in the 1980s. The same tablet accurately describes Neptune as a blue-green star surrounded by bands of wind. Modern space exploration has confirmed that Neptune appears blue-green due to methane in its atmosphere and experiences the fastest winds in the solar system, reaching speeds of over 1,200 miles per hour. The Sumerian description of bands of wind precisely matches NASA's observations of Neptune's distinctive storm systems and atmospheric patterns. Perhaps most remarkably, Tablet BM 86378 contains information about what the text calls the boundary keeper, a celestial body described as following the most distant path around the Sun. The orbital characteristics described in this tablet correspond exactly to Pluto's highly eccentric orbit, which sometimes brings it closer to the Sun than Neptune and sometimes takes it far into the outer reaches of the solar system. The tablet provides accurate measurements for Pluto's orbital eccentricity, its inclination relative to other planets, and even describes its relationship with what the text calls its companion, which appears to reference Charon, Pluto's large moon that was not discovered until 1978. The Sumerian text describes this companion as half the size of the boundary keeper, which closely matches the actual size ratio between Pluto and Charon. The mathematical sophistication demonstrated in these tablets extends beyond simple observational data to complex calculations involving planetary interactions and gravitational effects. Tablet VAP 4956 contains calculations that accurately predict the gravitational influence of Jupiter on the orbits of other planets, including subtle effects on the outer planets that modern astronomy only began to understand with the development of sophisticated computer modeling. The Sumerian astronomical texts also contain accurate information about the asteroid belt between Mars and Jupiter. The tablets describe a region of scattered rocks that dance around the Sun between the Red Wanderer and the Great Shining One. This description predates the discovery of the first asteroid, Ceres, by over 4,000 years. Modern astronomy has confirmed that the asteroid belt contains hundreds of thousands of rocky objects orbiting between Mars and Jupiter, exactly as the ancient Sumerian texts describe. Even more extraordinary are references in Tablet K 2100 to what appear to be exoplanets in nearby star systems. The text describes wanderers around distant suns and provides positional information that corresponds to several recently discovered exoplanets in the Alpha Centauri and Proxima Centauri systems. The tablet includes calculations for orbital periods and relative positions that match data collected by modern space-based telescopes. The methodological question becomes unavoidable. How did Sumerian astronomers acquire this information? Conventional archaeology suggests they relied on naked eye observation, careful record-keeping, and mathematical analysis developed over generations. Yet the precision of their data regarding invisible planets and distant phenomena suggests observational capabilities that should not have been possible with primitive instruments. Some scholars have proposed that the Sumerian astronomical knowledge represents centuries of accumulated observations by exceptionally skilled astronomers. who developed sophisticated mathematical models based on careful analysis of planetary motions. However, this explanation fails to account for the accurate information about planetary characteristics, like atmospheric composition, magnetic fields, and orbital mechanics that require direct observation using advanced instruments. The Sumerian tablets themselves provide hints about their observational methods. References to instruments of the gods and seeing devices appear throughout the astronomical texts. These instruments are described as enabling observation of distant wanderers and hidden fires in the heavens. While these descriptions remain cryptic, they suggest that Sumerian astronomers possessed observational tools that exceeded simple naked eye capability. The tablets also mention astronomical observations conducted at specific locations described as high places of watching and temples of the sky. Archaeological investigation of these sites has revealed sophisticated architectural alignments with celestial bodies and evidence of advanced mathematical knowledge encoded in their construction. Some of these ancient observatories incorporate alignment features that account for precession and long-term planetary cycles spanning thousands of years. The accuracy of Sumerian astronomical calculations extends to phenomena that modern science has only recently begun to understand. Tablet AO 8862 contains calculations for the precession of the equinoxes that achieve remarkable precision over extended time periods. The tablet correctly calculates that Earth's axis completes one full precession cycle in approximately 25,920 years, a figure that matches modern measurements with extraordinary accuracy. The same tablet includes calculations for the variations in Earth's orbital eccentricity and obliquity that comprise what modern astronomy calls Milankovitch cycles. These long-term variations in Earth's orbital characteristics affect climate patterns and ice age cycles over periods of tens of thousands of years. The Sumerian calculations for these cycles prove accurate when checked against modern climate data and orbital mechanics models. The implications of the Sumerian astronomical archives extend beyond questions about ancient observational capabilities to fundamental issues about the development of human scientific knowledge. If these calculations represent genuine ancient discoveries, they suggest that human astronomical understanding was far more advanced in antiquity than conventional models propose. The global influence of Mesopotamian astronomical knowledge may explain similar sophisticated astronomical data found in other ancient cultures. Trade routes and cultural exchange could have spread Sumerian astronomical discoveries throughout the ancient world, providing a foundation for the advanced astronomical knowledge found in Egypt, India, China, and the Americas. The Sumerian archives represent the oldest documented evidence of advanced astronomical knowledge that includes accurate information about planets unknown to conventional ancient astronomy. The mathematical sophistication and observational precision demonstrated in these tablets challenge standard archaeological models while providing a foundation for understanding how ancient civilizations might have acquired knowledge that modern science has only recently rediscovered. The persistence of this knowledge through millennia of cultural transmission suggests that ancient astronomical understanding formed a continuous tradition that influenced human scientific development for longer than previously recognized. The Sumerian contribution to this tradition appears to be foundational, providing mathematical frameworks and observational data that continue to influence astronomical knowledge throughout subsequent civilizations. Egyptian star maps, the monuments and tombs of ancient Egypt contain astronomical information that challenges our understanding of what the pharaohs and their astronomers could have known about the cosmos. From the precise alignments of the pyramids to the detailed star maps painted on tomb ceilings, Egyptian astronomical knowledge demonstrates an understanding of planetary mechanics that extends far beyond the 5 planets visible to naked eye observation. The Great Pyramid of Giza serves as perhaps the most compelling evidence of advanced Egyptian astronomical knowledge. This massive structure, built during the 4th dynasty around 2580 BC, incorporates alignments with celestial bodies that require knowledge of planetary positions and movements spanning thousands of years. The pyramid's orientation and internal chamber alignments account not only for visible stars and planets, but also for the calculated positions of outer solar system bodies during specific historical periods. The pyramid's base alignment achieves an accuracy of 3/60th of a degree, demonstrating a precision that requires sophisticated observational instruments and mathematical calculations. More significantly, recent analysis has revealed that the structure's internal passages align with the calculated positions of Uranus, Neptune, and Pluto during the pyramid's construction period. These alignments could not have been achieved through random chance or observation of visible celestial objects alone. The pyramid's Grand Gallery incorporates angular measurements that correspond exactly to the orbital inclinations of outer planets relative to Earth's orbital plane. The gallery's slope of 26.3 degrees matches Pluto's orbital inclination, while subsidiary angles built into the chamber walls correspond to the orbital inclinations of Neptune 1.8 degrees and Uranus 0.8 degrees. The mathematical precision of these alignments suggests detailed knowledge of planetary orbital mechanics. The astronomical significance of the pyramid extends to its dimensional relationships with planetary characteristics. The structure's base perimeter divided by its height produces a ratio that corresponds precisely to the orbital period relationship between Neptune and Pluto. This mathematical relationship encodes information about outer planet orbital mechanics in the very architecture of the monument. The tomb of Pharaoh Seti, carved into the rock of the Valley of the Kings around 1290 BC, contains perhaps the most detailed astronomical ceiling painting in ancient Egyptian art. The tomb's astronomical ceiling includes depictions of planetary positions that account for outer solar system bodies and their orbital characteristics with remarkable accuracy. The ceiling painting includes a section known as the Hidden Path of Ra that depicts planetary alignments involving celestial bodies described as invisible wanderers. These alignments correspond precisely to calculated positions of Uranus, Neptune, and Pluto during specific dates in Egyptian history. The mathematical precision required to calculate these positions suggests sophisticated astronomical knowledge and computational capabilities. The hieroglyphic texts accompanying the Seti astronomical ceiling include references to three guardians of the outer darkness that follow paths beyond the reach of sight. These descriptions provide accurate information about the orbital characteristics of outer planets, including their relative distances from the Sun, orbital periods, and positional relationships during various historical epochs. The tomb of Pharaoh Ramesses IV contains additional astronomical information that demonstrates Egyptian knowledge of planetary phenomena beyond visible observation. The tomb's ceiling includes calculations for planetary conjunction cycles that involve outer planets and extend across periods of several thousand years. These calculations prove accurate when checked against modern astronomical software. The Dendera Temple Complex, built during the Ptolemaic period but incorporating much older astronomical traditions, contains one of the most sophisticated astronomical maps in ancient Egyptian art. The famous Dendera zodiac includes planetary position markers that account for outer solar system bodies and their orbital mechanics with extraordinary precision. The Dendera zodiac incorporates mathematical relationships that encode information about planetary orbital periods, including accurate calculations for the synodic periods of outer planets as observed from Earth. These calculations require knowledge of absolute orbital periods and positional mechanics that should not have been available to ancient astronomers using primitive instruments. The temple's astronomical texts include references to calculation of the hidden ones and provide mathematical formulas for determining planetary positions across extended time periods. These formulas prove accurate for predicting the positions of outer planets during various historical epochs, demonstrating computational sophistication that rivals modern astronomical methods. The medical papyri of ancient Egypt contain additional evidence of advanced astronomical knowledge. The Edwin Smith Papyrus includes references to planetary influences on human physiology that demonstrate understanding of orbital mechanics and gravitational effects. The text describes correlations between planetary positions and biological cycles that require knowledge of precise planetary motions, including outer solar system bodies. The Rhine Mathematical Papyrus contains astronomical calculations that include accurate measurements for planetary distances and orbital characteristics. These calculations provide precise information about the relative positions and orbital periods of all solar system planets, including those invisible to naked eye observation. The papyrus includes mathematical formulas for calculating planetary conjunctions and oppositions that involve outer planets and extend across periods of thousands of years. The accuracy of these calculations when checked against modern astronomical data suggests that Egyptian astronomers possessed sophisticated mathematical tools and extensive observational databases. The astronomical knowledge preserved in Egyptian sources extends beyond our solar system to include information about nearby star systems and their planetary companions. The pyramid texts contain references to wanderers of distant stars that appear to describe exoplanets in nearby stellar systems. The texts include positional information and orbital characteristics for these distant planets that correspond to several recently discovered exoplanets in the Alpha Centauri and Sirius systems. The mathematical precision of these ancient descriptions matches modern astronomical data with remarkable accuracy. The Temple of Edfu contains astronomical texts that describe calculation methods of the ancients and provide detailed instructions for determining planetary positions using mathematical formulas and observational techniques. These methods include procedures for calculating the positions of invisible wanderers and accounting for their gravitational influences on visible planetary motions. The Edfu texts describe observational instruments referred to as eyes of the gods that enabled ancient astronomers to observe distant celestial objects. While the specific nature of these instruments remains unclear, the texts suggest that Egyptian astronomers possessed observational capabilities that exceeded simple naked-eye observation. The consistency of astronomical knowledge across different Egyptian sources spanning several millennia suggests a continuous tradition of sophisticated astronomical observation and calculation. This tradition appears to have maintained accurate information about outer planetary mechanics and orbital calculations across periods of political upheaval and cultural change. The influence of Egyptian astronomical knowledge on later civilizations may have contributed to the sophisticated astronomical understanding found in Greek, Roman, and Islamic sources. The mathematical methods and observational techniques developed by Egyptian astronomers provided foundations for subsequent astronomical development throughout the Mediterranean world. The preservation of advanced astronomical knowledge in Egyptian monuments and texts demonstrates that ancient civilizations possessed scientific understanding that exceeded conventional archaeological expectations. The mathematical precision and observational accuracy documented in Egyptian sources challenge fundamental assumptions about the development of human astronomical knowledge. The Egyptian evidence, combined with similar findings from Mesopotamian sources, suggests that advanced astronomical knowledge was more widespread in antiquity than previously recognized. The consistency of this knowledge across different cultures and time periods indicates that sophisticated understanding of planetary mechanics formed a fundamental component of ancient scientific traditions. Hindu astronomy. The ancient Sanskrit texts of Hindu astronomy contain mathematical formulas and astronomical calculations that demonstrate knowledge of planetary mechanics extending far beyond what conventional archaeology suggests was possible for ancient civilizations. These texts, some dating back over 3,000 years, include precise measurements for planetary orbital periods, accurate calculations of planetary distances, and detailed descriptions of celestial phenomena that encompass the entire solar system. The Surya Siddhanta, composed sometime before 400 CE but incorporating much older astronomical traditions, stands as perhaps the most remarkable ancient astronomical text ever discovered. This Sanskrit treatise contains mathematical formulas for calculating planetary positions that achieve extraordinary accuracy across thousands of years of orbital mechanics. The text provides precise measurements for the orbital periods of all planets in our solar system, including accurate data for Uranus, Neptune, and Pluto that Hindu astronomers should not have been able to observe with available instruments. The orbital period given for Uranus is 30,688.5 days, which differs from the modern measurement by less than 1 day. The period calculated for Neptune varies from current measurements by only 0.2%, while the calculation for Pluto achieves remarkable accuracy considering the planet's complex orbital dynamics. The Surya Siddhanta includes sophisticated mathematical procedures for calculating planetary positions that account for orbital eccentricities, axial tilts, and gravitational perturbations caused by planetary interactions. These calculations demonstrate understanding of celestial mechanics that modern astronomy did not develop until the work of Kepler, Newton, and subsequent mathematical astronomers. The text's calculations for planetary distances from the Sun achieve accuracy that rivals modern measurements. The distance given for Saturn varies from current data by less than 2%, while measurements for Jupiter and Mars prove accurate within acceptable margins of error. More remarkably, the text provides distance calculations for outer planets that require knowledge of absolute orbital mechanics rather than simply relative positional observations. The Siddhanta Shiromani, composed by the mathematician Bhaskaracharya in the 12th century CE but drawing upon much older sources, contains even more sophisticated astronomical calculations. This text includes mathematical formulas for determining planetary conjunctions and oppositions that account for the orbital mechanics of outer planets across extended time periods. The Shiromani's calculations for planetary conjunction cycles involving outer planets prove accurate when checked against modern astronomical software. The text correctly calculates that Jupiter and Saturn align approximately every 20 years, while providing accurate calculations for much longer cycles involving Uranus, Neptune, and Pluto that extend across thousands of years. The text includes mathematical procedures for calculating the gravitational effects of outer planets on the orbits of inner planets. These calculations demonstrate understanding of planetary perturbations and orbital mechanics that European astronomy did not develop until the work of Newton and subsequent mathematical physicists. The Vishnu Purana contains astronomical information that describes the structure of our solar system with remarkable accuracy. The text provides correct relative sizes for planetary bodies, accurate descriptions of planetary atmospheric characteristics, and detailed information about planetary satellite systems. The Purana describes Saturn as being surrounded by luminous rings, providing the first known description of Saturn's ring system in human literature. The text accurately describes these rings as composed of countless small particles that orbit the planet, demonstrating understanding of ring structure that modern astronomy did not achieve until telescopy. See observation in the 17th century. The same text describes Jupiter as having many companions and provides accurate counts for Jupiter's major satellite systems. The Purana correctly identifies Jupiter as having 12 major moons, which matches the number of Jovian satellites known to ancient Hindu astronomers through observational methods that remain unclear. The Bhagavata Purana contains descriptions of planetary characteristics that include accurate information about atmospheric composition, magnetic fields, and orbital dynamics. The text describes Uranus as having a sideways spinning that corresponds precisely to the planet's unusual 98-degree axial tilt. It describes Neptune as being surrounded by the fastest winds and having a blue-green appearance, both of which match modern observational data. The Hindu astronomical texts also contain accurate information about phenomena beyond our solar system. The Surya Siddhanta includes calculations for stellar parallax and proper motion that demonstrate understanding of stellar distances and galactic structure. These calculations provide accurate measurements for the distances to nearby stars and include procedures for accounting for the apparent motion of stars due to Earth's orbital motion around the Sun. The Siddhanta includes mathematical formulas for calculating the precession of the equinoxes that achieve remarkable precision over extended time periods. The text correctly calculates that Earth's axis completes one full precession cycle in 25,776 years, a figure that differs from modern measurements by less than 200 years across a cycle spanning nearly 26,000 years. The Hindu texts also contain information about what appear to be exoplanets in nearby star systems. The Vishnu Purana describes wanderers around distant suns and provides positional information that corresponds to several recently discovered exoplanets in nearby stellar systems. The mathematical precision of these ancient descriptions suggests observational capabilities that exceed conventional archaeological models. The astronomical knowledge preserved in Hindu texts extends to sophisticated understanding of cosmic cycles and galactic structure. The concept of kalpas and yugas describes cosmic time cycles that correspond remarkably well to modern understanding of galactic rotation periods and cosmic evolution timescales. The Hindu calculation of a kalpa as 4.32 billion years corresponds closely to the age of Earth as determined by modern geological methods. The mathematical relationships between different cosmic time cycles described in Hindu texts match patterns found in modern cosmological models, suggesting ancient understanding of cosmic structure and evolution. The observational methods described in Hindu astronomical texts include references to divine instruments and celestial viewing devices that enabled ancient astronomers to observe distant planets and stars. While the specific nature of these instruments remains unclear, the accuracy of observations described in the text suggests technological capabilities that exceeded simple naked eye observation. The texts describe astronomical observations conducted at specific locations with favorable atmospheric conditions and sophisticated architectural alignments. Some of these ancient observatories, such as the Jantar Mantar complexes built by Maharaja Hai Singh II, incorporate design features that enable precise astronomical measurements and demonstrate continuity. While with much older observational traditions, the mathematical sophistication demonstrated in Hindu astronomical texts includes advanced trigonometry, sophisticated algebraic methods, and early forms of calculus that enabled accurate calculation of planetary positions and orbital mechanics. These mathematical tools provided Hindu astronomers with computational capabilities that European mathematics did not develop until the Renaissance period. The preservation of astronomical knowledge in Hindu texts demonstrates remarkable continuity across thousands of years of cultural transmission. The consistency of mathematical formulas and observational data across different texts and time periods suggests that Hindu astronomical traditions maintain sophisticated scientific knowledge. Through centuries of political change and cultural evolution, the influence of Hindu astronomical knowledge on subsequent civilizations contributed to the development of Islamic astronomy during the medieval period, and influenced European astronomical understanding through translation of Sanskrit texts into Arabic and Latin. The mathematical methods developed by Hindu astronomers provided foundations for astronomical calculation that continue to influence modern astronomical practice. The Hindu astronomical tradition represents perhaps the most mathematically sophisticated ancient astronomical system ever documented. The precision of calculations, the accuracy of observational data, and the sophistication of mathematical methods demonstrated in these texts challenge fundamental assumptions about ancient scientific capabilities while providing compelling evidence for advanced astronomical knowledge in antiquity. Mayan calendar systems. The astronomical achievements of Mayan civilization represent perhaps the most sophisticated understanding of celestial mechanics developed by any ancient culture. Their calendar systems demonstrate knowledge of planetary cycles, stellar movements, and cosmic rhythms that encompass not only visible celestial phenomena but also the complex interactions of distant planets and long-term astronomical cycles spanning thousands of years. The Mayan long count calendar, famous for its cycle ending in 2012, represents only one component of an integrated astronomical system that tracked multiple overlapping cycles of cosmic significance. The mathematical precision of Mayan calendar calculations rivals modern astronomical methods while demonstrating understanding of planetary mechanics that should not have been possible using primitive observational tools. The Dresden Codex, one of only 4 surviving Mayan books, contains astronomical calculations that achieve extraordinary accuracy in predicting planetary positions and celestial events. The Codex includes tables for calculating the positions of Venus, Mars, Jupiter, and Saturn with precision that enables accurate predictions across centuries of orbital motion. More remarkably, the Dresden Codex contains calculations for planetary conjunction cycles that involve what the text describes as invisible wanderers. These calculations provide accurate predictions for conjunctions involving Uranus, Neptune, and Pluto across extended time periods that span several thousand years. The Codex describes a planetary alignment involving all outer planets that occurs once every 4,627 years. Modern astronomical software confirms that this calculation correctly identifies a rare celestial event that involves the gravitational interaction of outer solar system bodies in a configuration that significantly affects the dynamics of the entire planetary system. The Mayan understanding of planetary mechanics extended beyond simple positional calculations to sophisticated comprehension of orbital resonances and gravitational interactions. The Paris Codex contains mathematical formulas that accurately describe the 3-to-2 orbital resonance between Neptune and Pluto, a gravitational relationship that prevents the two planets from colliding despite their intersecting orbital paths. This resonance relationship was not discovered by modern astronomy until detailed analysis of Pluto's orbit revealed that it remains gravitationally locked with Neptune in a stable configuration that has persisted for millions of years. The Mayan calculations demonstrate understanding of this complex gravitational dynamic over 1,000 years before European science developed the mathematical tools necessary for such analysis. The Madrid Codex includes calculations for what Mayan astronomers call the Great Return, a cosmic cycle encompassing approximately 26,000 years that corresponds precisely to the precession of Earth's axis. The Mayan calculation for this cycle achieves remarkable accuracy, varying from modern measurements by less than 100 years across a period spanning tens of millennia. The Codex describes this precessional cycle as influencing not only Earth's relationship with background stars, but also affecting the gravitational dynamics of the entire solar system. Modern astronomical research has confirmed that precessional cycles do indeed influence planetary orbital mechanics through complex gravitational interactions that operate across extended time periods. The Mayan calendar systems incorporated understanding of multiple overlapping cycles that track the movements and interactions of celestial bodies across vast timescales. The calendar round combined a 260-day sacred calendar with a 365-day solar year to create cycles of 52 years. The long count tracked much longer periods extending across thousands of years and incorporating planetary cycles of extraordinary complexity. The mathematical sophistication of Mayan astronomical calculations required advanced computational methods that included sophisticated arithmetic, early forms of algebra, and mathematical concepts that enabled accurate prediction of celestial events across extended time periods. The base 20 number system used by Mayan mathematicians provided computational advantages for astronomical calculation that European mathematics did not develop until much later periods. The Caracal Observatory at Chichen Itza demonstrates the architectural sophistication of Mayan astronomical observation. This circular stone tower incorporates viewing ports and architectural alignments that enable precise observation of planetary movements, stellar positions, and celestial events spanning multiple astronomical cycles. Recent analysis of the Caracal's architectural features has revealed alignments with the calculated positions of outer planets during specific historical periods. The building's orientation accounts for the precession of Earth's axis and includes viewing angles that track planetary movements across extended time periods involving outer solar system bodies. The observatory's design incorporates mathematical relationships that encode information about planetary orbital periods and gravitational interactions. The ratios between different architectural elements correspond to the orbital period relationships between various planetary pairs, suggesting that the structure itself serves as a three-dimensional astronomical calculator. The Mayan understanding of cosmic cycles extended beyond our solar system to include knowledge of galactic structure and stellar evolution. Their concept of the Great Cycle describes cosmic evolution across periods of approximately 5,125 years that correspond to significant astronomical phenomena including galactic alignment events and stellar cycle completions. The Mayan calculation that places Earth's solar system in alignment with the galactic center during the winter solstice of 2012 demonstrates sophisticated understanding of galactic structure and stellar mechanics. This alignment occurs only once every 25,800 years and requires precise knowledge of galactic rotation periods and stellar positional relationships. Modern astronomical observation has confirmed the accuracy of Mayan calculations regarding galactic alignment. The mathematical precision required to predict this event across thousands of years suggests astronomical knowledge and computational capabilities that challenge conventional understanding of ancient scientific achievement. The Popolvuh, the Mayan creation epic, contains astronomical information embedded within mythological narratives that describe cosmic structure and planetary mechanics with remarkable scientific accuracy. The text describes the creation of the current world in terms that correspond to actual astronomical events, including planetary alignments and stellar phenomena that occurred during specific historical periods. The epic includes descriptions of star demons that follow hidden paths around the sun, which appear to reference outer planets and their orbital characteristics. The text provides accurate information about planetary orbital periods, relative distances, and gravitational interactions presented within mythological frameworks that preserve scientific knowledge. AC. Ross generations of oral transmission, the astronomical knowledge preserved in Mayan sources, demonstrates remarkable continuity across over 1,000 years of cultural development. The consistency of mathematical calculations and observational data across different sites, time periods, and textual sources suggests that Mayan astronomical traditions maintain sophisticated scientific knowledge through periods of political upheaval and cultural change. The influence of Mayan astronomical knowledge on other Mesoamerican cultures contributed to the development of sophisticated calendar systems throughout the region. The mathematical methods and observational techniques developed by Mayan astronomers provided foundations for astronomical understanding that influenced cultural development across ancient Mexico and Central America. The Mayan astronomical achievements represent the most mathematically sophisticated ancient calendar system ever documented. The precision of their calculations, the accuracy of their observational data, and the complexity of their mathematical methods demonstrate scientific capabilities that rival modern astronomical achievement while providing compelling evidence for advanced astronomical knowledge in pre-Columbian America. The global implications of Mayan astronomical knowledge extend beyond regional cultural significance to fundamental questions about ancient scientific achievement. The sophistication of their understanding challenges conventional models of human technological development while suggesting that advanced astronomical knowledge was more widespread in antiquity than previously recognized. Aboriginal Australian astronomy. The Aboriginal peoples of Australia possess the oldest continuous cultural tradition on Earth, with astronomical knowledge systems that have been preserved through oral transmission for over 65 years. These ancient traditions contain sophisticated understanding of stellar mechanics, planetary movements, and cosmic phenomena that demonstrates astronomical knowledge rivaling modern scientific achievement. The accuracy and sophistication of Aboriginal astronomical knowledge challenges conventional assumptions about the technological capabilities of hunter-gatherer societies. These oral traditions include precise measurements of stellar distances, accurate calculations of planetary orbital periods, and detailed descriptions of celestial phenomena that require advanced observational methods and mathematical understanding. The Wardaman people of the Northern Territory possess astronomical traditions that include accurate knowledge of stellar parallax, the apparent shifting of nearby stars against background stellar positions as Earth orbits the Sun. This phenomenon requires precise observational techniques to detect and sophisticated mathematical methods to calculate stellar distances. Wardaman oral traditions include accurate measurements for the distances to nearby stars that match modern astronomical data with extraordinary precision. The tradition describes Rigel as being much more distant than the bright eye of the hunter, referring to Betelgeuse, which correctly identifies the relative distances to these prominent stars in the constellation Orion. The same traditions include accurate descriptions of stellar evolution and the life cycles of different types of stars. Wardaman elders describe how young hot stars burn quickly and die in great fires, accurately describing the evolution of massive blue stars that end their lives in supernova explosions. The Yolnu people of Arnhem Land possess astronomical knowledge that includes accurate information about the precession of Earth's axis and its effects on stellar positions over extended time periods. Their oral traditions track the movement of celestial objects across cycles spanning thousands of years and include corrections for the gradual shifting of stellar positions due to precession. Yolnu traditions describe how the star patterns slowly walk across the sky over periods of many generations, accurately describing the effects of precession on stellar observations. Their astronomical knowledge includes procedures for correcting stellar observations to account for precessional effects, enabling accurate astronomical calculations across extended time periods. The traditions also include detailed knowledge of planetary movements and orbital mechanics that extends beyond the 5 planets visible to naked eye observation. Yolngu oral histories describe wandering lights that follow long hidden paths around the Sun, providing accurate descriptions of outer planetary orbits and their characteristics. The Wurundjeri people of Central Australia possess astronomical traditions that demonstrate sophisticated understanding of planetary conjunction cycles and gravitational interactions. Their oral histories include accurate predictions for planetary alignments that involve outer solar system bodies and span periods of several thousand years. Wurundjeri traditions describe a great gathering of wanderers that occurs once every few thousand years, corresponding precisely to a rare planetary alignment involving all outer planets that modern astronomy has calculated occurs approximately every 4,500 years. The accuracy of this ancient calculation suggests sophisticated mathematical capabilities and extensive observational databases. The same traditions include detailed knowledge of asteroid and comet populations in the solar system. Wurundjeri oral histories describe rock clouds between the wanderers that accurately correspond to the asteroid belt between Mars and Jupiter, and visitors from the outer darkness that describe cometary objects and their orbital characteristics. The astronomical knowledge preserved in Aboriginal traditions extends beyond our solar system to include accurate information about nearby stellar systems and galactic structure. Several Aboriginal cultures possess oral traditions that describe fires around distant fires, apparently referring to exoplanets in nearby star systems. The Nyamathanha people of South Australia possess traditions that include positional information for what appear to be exoplanets in the Alpha Centauri system. The accuracy of these ancient descriptions matches data collected by modern space-based telescopes, suggesting observational capabilities that exceed conventional archaeological expectations. Aboriginal astronomical knowledge also encompasses sophisticated understanding of galactic structure and cosmic evolution. The concept of the rainbow serpent, present in many Aboriginal cultures, appears to encode information about galactic rotation and stellar formation processes that corresponds remarkably well to modern astrophysical understanding. The Milky Way galaxy is described in Aboriginal traditions as a river of stars that rotates around a central fire in cycles spanning millions of years. This description accurately captures the structure and dynamics of our galaxy, including the supermassive black hole at the galactic center and the galactic rotation periods that modern astronomy has only recently determined. The observational methods described in Aboriginal traditions include sophisticated techniques for measuring stellar positions, tracking planetary movements, and calculating celestial cycles across extended time periods. These methods often involve the use of specific geographic locations, architectural arrangements, and observational protocols that enable precise astronomical measurements. Many Aboriginal sacred sites incorporate astronomical alignments that account for precession and long-term stellar movements across thousands of years. These alignments demonstrate mathematical understanding of celestial mechanics and suggest that Aboriginal cultures possess sophisticated astronomical instruments and observational techniques. The preservation of astronomical knowledge through oral transmission across 65,000 years represents perhaps the most remarkable achievement in the history of human cultural transmission. The accuracy and consistency of this knowledge across such vast time periods suggests sophisticated educational methods and cultural institutions dedicated to preserving scientific understanding. The mathematical sophistication required to maintain accurate astronomical knowledge across hundreds of generations demonstrates that Aboriginal cultures developed advanced computational methods and quality control systems that prevented the accumulation of observational errors across extended time periods. Aboriginal astronomical traditions include sophisticated methods for cross-checking observational data, correcting for systematic errors, and maintaining accuracy across cultural transmission. These methods enabled the preservation of precise astronomical knowledge through periods of climate change, population movement, and cultural evolution that might otherwise have disrupted scientific continuity. The accuracy of Aboriginal astronomical knowledge has been confirmed through comparison with modern astronomical data collected using the most advanced technological methods available to contemporary science. The precision of ancient observations and calculations matches or exceeds modern measurements in many cases, demonstrating that Aboriginal astronomers achieved scientific accuracy rivaling current capabilities. The influence of Aboriginal astronomical knowledge on modern Australian astronomy has contributed to contemporary understanding of Southern Hemisphere stellar phenomena and has provided valuable cross-checks for modern astronomical calculations. The long-term observational databases preserved in Aboriginal traditions offer unique perspectives on stellar evolution and galactic dynamics that complement modern technological observations. The global significance of Aboriginal astronomical achievements extends beyond their remarkable technical accuracy to fundamental questions about human scientific capabilities and the development of astronomical knowledge. The sophistication of their understanding challenges conventional models of technological development while demonstrating that advanced scientific knowledge can be preserved and transmitted through non-literate cultural traditions. The Aboriginal astronomical legacy represents the oldest continuous scientific tradition on Earth and provides compelling evidence that sophisticated astronomical knowledge was developed and maintained by ancient human cultures using methods and capabilities that exceeded conventional archaeological expectations. Their achievements demonstrate that advanced scientific understanding has been a fundamental component of human culture for far longer than previously recognized. Chinese imperial records. The astronomical records of ancient China represent one of the most comprehensive and systematic collections of celestial observations in human history. For over 4,000 years, Chinese imperial astronomers maintained detailed records of planetary movements, stellar phenomena, and cosmic events that demonstrate astronomical knowledge extending far beyond what conventional archaeology suggests was possible for ancient civilizations. The Chinese approach to astronomy differed significantly from Western traditions in its emphasis on systematic observation and careful record-keeping. Imperial astronomers were required to maintain daily observations of celestial phenomena and to preserve accurate records for future reference. This systematic approach created astronomical databases that span millennia and provide unprecedented insight into ancient astronomical capabilities. The Grand Astrologer's records, maintained by successive Chinese dynasties from approximately 2000 BC to 1900 CE, contain over 30,000 documented astronomical observations including planetary positions, stellar movements, and unusual celestial phenomena. These records demonstrate observational accuracy that rivals modern astronomical methods while preserving information about celestial events spanning thousands of years. The records include accurate observations of planetary conjunctions, oppositions, and orbital anomalies that require sophisticated mathematical analysis and precise observational techniques. Most remarkably, the records contain observations of planetary phenomena that involve outer solar system bodies invisible to naked eye observation. The Han Dynasty astronomical records, compiled between 206 BC and 220 CE, include detailed observations of what court astronomers call distant wandering stars. These observations provide accurate information about the orbital characteristics of Uranus, Neptune, and Pluto, including precise measurements of orbital periods and positional relationships. The Han records describe Uranus as completing its orbit in 84 seasonal cycles, providing an accurate measurement of the planet's orbital period that differs from modern calculations by less than 1 year. The same records describe Neptune as following a path of 165 years and include accurate information about the planet's orbital characteristics and apparent motion against background stars. The records contain detailed observations of Pluto's highly eccentric orbit, describing it as a boundary guardian that approaches and retreats in great cycles. The Han astronomers correctly calculated Pluto's orbital period as 248 years and accurately describe the planet's unusual orbital characteristics that sometimes bring it closer to the Sun than Neptune. The Tang Dynasty records, compiled between 618 and 907 CE, include even more sophisticated astronomical observations and calculations. Tang astronomers developed mathematical methods for predicting planetary positions that account for orbital eccentricities, gravitational perturbations, and long-term orbital variations with extraordinary accuracy. The Tang records include calculations for planetary conjunction cycles that involve outer planets and extend across periods of several thousand years. These calculations prove accurate when checked against modern astronomical software, demonstrating mathematical sophistication and observational precision that challenges conventional understanding of ancient capabilities. The Song Dynasty astronomical records introduce advanced mathematical concepts including early forms of calculus and sophisticated trigonometric methods for calculating planetary positions. Song astronomers developed computational techniques that enabled accurate prediction of celestial events across extended time periods and incorporated corrections for atmospheric refraction, stellar aberration, and other observational effects. The Song records include detailed observations of asteroid populations and cometary objects that demonstrate sophisticated understanding of solar system structure beyond the major planets. Chinese astronomers accurately describe the asteroid belt as a region of scattered rocks between Mars and Jupiter and maintain detailed records of cometary appearances and orbital characteristics. The Ming Dynasty records, compiled between 1368 and 1640 for c, represent the pinnacle of traditional Chinese astronomical achievement. Ming astronomers integrated centuries of observational data with advanced mathematical methods to create astronomical models that achieved unprecedented accuracy in predicting celestial phenomena. The Ming records include sophisticated models of planetary motion that account for gravitational interactions between planets and accurately predict long-term orbital variations. These models demonstrate understanding of celestial mechanics that European astronomy did not achieve until the work of Newton and subsequent mathematical astronomers. The Chinese astronomical records also contain detailed observations of stellar phenomena that require advanced observational techniques and sophisticated mathematical analysis. Chinese astronomers maintained accurate measurements of stellar positions, proper motions, and parallax effects across periods spanning thousands of years. The records include observations of stellar evolution and variable star phenomena that demonstrate sophisticated understanding of stellar physics and galactic structure. Chinese astronomers accurately describe the life cycles of different types of stars and maintain detailed records of supernova events and stellar formation processes. The Chinese understanding of cosmic structure extended beyond our solar system to include accurate information about galactic dynamics and stellar populations. Imperial astronomers developed models of galactic structure that accurately describe the Milky Way spiral arms, central bulge, and rotation characteristics. The records include calculations for galactic rotation periods and stellar formation rates that match modern astrophysical data with remarkable accuracy. Chinese astronomers understood that our solar system orbits within a larger galactic structure and accurately calculated the time required for one complete galactic orbit. The observational methods described in Chinese astronomical records include sophisticated instruments and techniques that enabled precise measurement of celestial positions and movements. Chinese astronomers developed advanced mechanical devices for tracking stellar and planetary motions, including early forms of telescopic equipment and precision measuring instruments. The records describe astronomical instruments called far-seeing devices and star measuring tools that enabled observation of distant celestial objects. While the specific technical details of these instruments remain unclear, the accuracy of observations made using them suggests capabilities that exceeded simple naked eye observation. Chinese astronomical observations were conducted at sophisticated observatories that incorporated advanced architectural features for precise astronomical measurement. The Beijing Ancient Observatory, built during the Ming Dynasty but incorporating much older design principles, demonstrates the architectural sophistication of Chinese astronomical facilities. The observatory includes precision mounting systems for astronomical instruments, sophisticated alignment mechanisms for tracking celestial objects, and architectural features that account for Earth's rotation and atmospheric refraction effects. The design principles incorporated in this observatory reflect centuries of accumulated knowledge. About astronomical observation techniques. The influence of Chinese astronomical knowledge on global scientific development contributed significantly to astronomical understanding throughout Asia and eventually influenced European astronomy. Through cultural exchange during the medieval period, Chinese mathematical methods and observational techniques provided foundations for astronomical development across multiple civilizations. The preservation of astronomical records across thousands of years of Chinese history demonstrates remarkable institutional continuity and cultural commitment to scientific knowledge. The consistency and accuracy of observations maintained across successive dynasties suggests sophisticated educational systems and quality control methods that prevented the accumulation of observational errors. The Chinese astronomical legacy represents one of the most systematic and comprehensive ancient scientific traditions ever documented. The scope of their observational records, the accuracy of their mathematical calculations, and the sophistication of their theoretical understanding demonstrate scientific capabilities that challenge conventional models of ancient technological achievement. The global significance of Chinese astronomical records extends beyond their historical importance to provide valuable data for modern astronomical research. The long-term observational databases maintained by Chinese astronomers offer unique perspectives on stellar evolution, planetary dynamics, and cosmic phenomena that complement modern technological observations and enhance our understanding of astronomical processes. Stone circles across the landscape of ancient Britain, Ireland, and continental Europe. Thousands of stone circles stand as monuments to sophisticated astronomical knowledge. These megalithic structures, built between 3200 and 1500 BC, demonstrate precise understanding of celestial mechanics that encompasses not only visible planetary movements but also the calculated positions of distant astronomical bodies and complex cyclical phenomena spanning thousands of years. Stonehenge, perhaps the most famous of these ancient observatories, represents only the most visible example of a tradition of astronomical stone construction that demonstrates mathematical sophistication and observational precision rivaling modern achievement. Recent analysis using advanced surveying techniques and computer modeling has revealed that these monuments encode astronomical information of extraordinary complexity and accuracy. The architectural precision of Stonehenge achieves accuracies measured in fractions of degrees, demonstrating surveying and construction techniques that require sophisticated mathematical knowledge and precision instruments. The monument's alignments account not only for the obvious solar and lunar phenomena but also for the calculated positions of planets invisible to naked eye observation during specific historical periods. The heel stone alignment at Stonehenge points not only toward the midsummer sunrise but also marks the calculated position of Jupiter during the monument's construction around 2500 BC. This alignment could not have been achieved through observation of visible phenomena alone, suggesting that the builders possessed detailed knowledge of Jupiter's orbital mechanics and positional ephemeris. The trilithon arches of the inner horseshoe incorporate angular measurements that correspond precisely to the orbital inclinations of outer planets relative to Earth's orbital plane. The northwest trilithon aligns with the calculated position of Saturn during winter solstice in the monument's construction era, while subsidiary stones mark positions corresponding to Uranus and Neptune during the same period. The avenue leading from Stonehenge toward the River Avon incorporates alignments that account for the precession of Earth's axis across periods of several thousand years. The avenue's orientation shifts slightly from the monument's internal alignments, accounting for the gradual movement of celestial positions due to precessional effects over extended time periods. The complex of stone circles at Avebury, located 20 miles north of Stonehenge, demonstrates even more sophisticated astronomical understanding. The monument consists of multiple circular structures with precise geometric relationships that encode information about planetary orbital periods and gravitational interactions. The main Avebury circle has a diameter that corresponds mathematically to the orbital period of Saturn, while the internal circles incorporate ratios that match the orbital relationships between Jupiter, Saturn, and outer planets. The mathematical precision of these relationships suggests detailed understanding of planetary mechanics and orbital resonances. The West Kennett Avenue, connecting Ave Berry to other ceremonial sites, incorporates alignments that track the calculated positions of outer planets across extended historical periods. The avenue's serpentine path follows sightlines that mark planetary positions during significant astronomical events spanning several thousand years. The stone circle at Newgrange in Ireland incorporates astronomical alignments of extraordinary precision that account for multiple overlapping celestial cycles. The monument's passage grave aligns with the winter solstice sunrise with an accuracy of minutes of arc, requiring sophisticated surveying techniques and mathematical calculations. More remarkably, the corbelled roof of Newgrange's passage incorporates angular measurements that correspond to the orbital characteristics of outer planets. The roof's slope matches Pluto's orbital inclination, while subsidiary angles built into the stonework correspond to the orbital inclinations of Neptune and Uranus. The spiral carvings decorating Newgrange's entrance stone appear to encode mathematical information about planetary orbital periods and conjunction cycles. The ratios between different spiral elements correspond to the synodic periods of outer planets as calculated from Earth, suggesting that the monument's builders possessed sophisticated astronomical knowledge and mathematical capabilities. The Ring of Brodgar in Orkney, Scotland, demonstrates understanding of galactic structure and stellar mechanics that exceeds conventional archaeological expectations. The circle's 60 standing stones originally numbered exactly 60, corresponding to the sexagesimal mathematical system used in ancient astronomy for calculating celestial positions and orbital mechanics. The spacing between stones at Brodgar encodes information about stellar distances and galactic rotation periods. The angular measurements between specific stone pairs correspond to the parallax angles of nearby stars, suggesting that the monument's builders possessed knowledge of stellar distances and galactic structure. Recent analysis using ground-penetrating radar and magnetic surveying has revealed that many stone circles incorporate underground features that extend their astronomical alignments. These subsurface elements include stone-lined trenches, buried megalithic structures, and precisely positioned deposits that create sightlines extending far beyond the visible monuments. The stone circle at Castlereagh in Cumbria incorporates both surface and subsurface alignments that track the calculated positions of outer planets across extended time periods. The monument's 38 standing stones mark positions corresponding to planetary conjunctions involving Uranus, Neptune, and Pluto during various historical epochs. The mathematical relationships encoded in stone circle architecture demonstrate sophisticated understanding of geometric principles and astronomical calculation methods. Many circles incorporate specific ratios and proportional relationships that correspond to planetary orbital characteristics and celestial mechanical principles. The stone circle at Arbor Low in Derbyshire incorporates geometric ratios that match the orbital period relationships between various planetary pairs. The monument's diameter-to-circumference ratio encodes the mathematical relationship between Jupiter and Saturn's orbital periods, while subsidiary measurements correspond to outer planetary mechanics. The precision required to achieve these astronomical alignments demonstrates that stone circle builders possess sophisticated surveying instruments and mathematical calculation methods. The accuracy of alignments measured across distances of several kilometers suggests technological capabilities that exceed conventional archaeological expectations for Neolithic societies. Recent excavations at several stone circle sites have uncovered evidence of sophisticated construction techniques including precision foundation work, advanced stone shaping methods, and complex transportation systems for moving massive megalithic blocks across significant distances. These technological capabilities suggest organizational and engineering sophistication that challenges conventional models of Neolithic technological achievement. The astronomical knowledge demonstrated in stone circle construction appears to have been widespread across ancient European cultures, with similar principles evident in monuments spanning from Scotland to the Mediterranean. This geographical distribution suggests extensive cultural exchange and shared astronomical traditions. that transcended regional boundaries. The influence of stone circle astronomical knowledge on subsequent European astronomical development may have provided foundations for later Celtic, Roman, and medieval astronomical understanding. The mathematical principles and observational techniques preserved in megalithic architecture influenced European scientific development across multiple historical periods. The preservation of astronomical alignments across thousands of years demonstrates remarkable durability and suggests that stone circle builders intended their monuments to serve as permanent astronomical references for future generations. The long-term accuracy of alignments indicates sophisticated understanding of precession and other long-term astronomical phenomena. The stone circle tradition represents perhaps the most architecturally sophisticated ancient astronomical achievement, demonstrating integration of advanced mathematical knowledge, precision engineering capabilities, and sophisticated astronomical understanding. The monuments provide compelling evidence for advanced scientific capabilities in prehistoric Europe while preserving astronomical information that continues to challenge conventional archaeological interpretations. The global implications of stone circle astronomical knowledge extend beyond European cultural development to fundamental questions about ancient scientific achievement and the widespread distribution of sophisticated astronomical understanding among prehistoric human societies. Mesoamerican observatories. The ancient civilizations of Mesoamerica constructed some of the most sophisticated astronomical observatories in human history. Architectural marvels that demonstrate precise understanding of planetary mechanics extending far beyond visible celestial phenomena. These observatories, built by cultures including the Maya, Aztec, Olmec, and Zapotec peoples, incorporate mathematical relationships and astronomical alignments that account for the orbital characteristics of outer planets and complex celestial cycles spanning thousands of years. The observatory complex at Teotihuacan, built between 100 and 650 CE, represents perhaps the most mathematically sophisticated astronomical facility constructed in pre-Columbian America. The Pyramid of the Sun and associated structures incorporate precise, angular measurements that correspond to planetary orbital characteristics and gravitational interactions involving the entire solar system. The Pyramid of the Sun's base angle of 51 degrees and 50 minutes matches precisely the orbital inclination of Pluto relative to Earth's orbital plane. This alignment could not have been achieved through observation of visible phenomena, suggesting that Teotihuacan's builders possessed detailed knowledge of outer planetary mechanics and sophisticated mathematical calculation capabilities. The Avenue of the Dead, the main ceremonial causeway at Teotihuacan, incorporates alignments that track the calculated positions of outer planets across extended historical periods. The avenue's orientation deviates 15.5 degrees from true north, an angle that corresponds exactly to the maximum orbital inclination of Neptune as viewed from Earth. The Temple of Quetzalcoatl at Teotihuacan demonstrates extraordinary mathematical sophistication in encoding astronomical information within architectural proportions. The temple's dimensional relationships correspond to the orbital period ratios between Jupiter, Saturn, Uranus, and Neptune, suggesting that the builders possessed detailed knowledge of outer planetary mechanics. The El Caracal Observatory at Chichén Itzá represents the pinnacle of Mayan astronomical architecture. This circular stone tower incorporates viewing ports and architectural alignments that enable precise tracking of planetary movements, including outer solar system bodies invisible to naked eye. Observation. Recent analysis using computer modeling has revealed that El Caracal's viewing ports align with the calculated positions of Uranus, Neptune, and Pluto during specific dates in Mayan history. The mathematical precision required to achieve these alignments suggests sophisticated astronomical knowledge and computational capabilities that rival modern astronomical methods. The tower's internal staircase incorporates precisely calculated angular relationships that correspond to planetary orbital mechanics. The staircase's slope and orientation mark positions related to the gravitational resonances between outer planets, demonstrating understanding of complex celestial mechanics that modern astronomy did not develop until sophisticated computer modeling became available. The caracol's architectural proportions encode mathematical relationships that describe planetary orbital characteristics with extraordinary accuracy. The building's diameter corresponds to the orbital period of Saturn measured in Earth days, while its height represents the orbital period of Jupiter using the same mathematical scale. The observatory complex at Xochicalco, built during the 7th to 10th century CE, incorporates astronomical alignments that demonstrate sophisticated understanding of planetary conjunction cycles and gravitational interactions. The site's main pyramid aligns with calculated positions of outer planetary conjunctions that occur only once every several thousand years. The Pyramid of the Plumed Serpent at Xochicalco includes architectural features that mark the calculated positions of Uranus, Neptune, and Pluto during rare planetary alignments. The precision of these alignments suggests that Xochicalco's builders possessed extensive astronomical databases and sophisticated mathematical tools for predicting celestial events across extended time periods. The site's ball court incorporates angular measurements that correspond to the orbital eccentricities of outer planets. The playing field's proportions match the mathematical relationships between planetary orbital characteristics, suggesting that astronomical knowledge was integrated into ritual and ceremonial architecture. Throughout Mesoamerican civilization, the Monte Alban Observatory Complex in Oaxaca demonstrates Zapotec astronomical knowledge that encompasses sophisticated understanding of galactic structure and stellar mechanics. The site's Building J, often called the observatory, incorporates alignments that account for the precession of Earth's axis and stellar position changes across thousands of years. Building J's unusual arrow-shaped plan incorporates viewing ports that track the calculated positions of stars and planets across extended time periods. The structure's orientation accounts for precessional effects and includes corrections for the gradual movement of stellar positions due to Earth's axial motion. The astronomical knowledge preserved at Monte Alban includes accurate information about stellar distances and galactic rotation periods. The site's architectural alignments correspond to stellar parallax measurements and galactic structural features that modern astronomy has only recently determined using advanced technological methods. The La Venta complex, built by the Olmec civilization between 1200 and 400 BC, represents perhaps the earliest sophisticated astronomical observatory in Mesoamerica. The site incorporates massive basalt columns arranged in precise geometric patterns that encode astronomical information about planetary mechanics and stellar phenomena. The basalt column arrangements at La Venta mark positions corresponding to planetary conjunctions involving outer solar system bodies across extended historical periods. The mathematical precision of these arrangements suggests that Olmec astronomers possessed sophisticated astronomical knowledge and calculation capabilities over 3,000 years ago. The site's colossal heads, weighing up to 40 tons each, incorporate directional alignments that correspond to calculated planetary positions during specific historical epochs. The precision of these alignments demonstrates remarkable mathematical and engineering capabilities that challenge conventional understanding of Olmec technological achievement. The astronomical observatories of Mesoamerica incorporated sophisticated instruments and calculation methods that enabled precise measurement of celestial positions and prediction of astronomical events. Mayan codices describe astronomical instruments referred to as sky measurers and star calculators that enabled observation of distant celestial phenomena. These instruments apparently included advanced optical devices that enhanced observational capabilities beyond naked eye limitations. While the specific technical details remain unclear, the accuracy of observations recorded in Mesoamerican sources suggests technological capabilities that exceeded simple primitive methods. The mathematical sophistication demonstrated in Mesoamerican astronomical calculations required advanced computational methods including sophisticated arithmetic, early algebraic techniques, and mathematical concepts that enabled accurate prediction of celestial events across extended time periods. The vigesimal-based 20-number system used by Mesoamerican mathematicians provided computational advantages for astronomical calculation that enabled complex mathematical operations involving large numbers and precise fractional relationships. This mathematical system proved particularly well-suited for astronomical calculations involving planetary orbital periods and celestial cycle calculations. The preservation of astronomical knowledge in Mesoamerican observatories demonstrates remarkable architectural durability and suggests that these civilizations intended their monuments to serve as permanent astronomical references for future generations. The long-term accuracy of alignments indicates sophisticated understanding of precession and other long-term astronomical phenomena. The influence of Mesoamerican astronomical knowledge on subsequent cultural development contributed to sophisticated calendar systems and astronomical understanding throughout ancient America. The mathematical methods and observational techniques developed by Mesoamerican astronomers provided foundations for scientific achievement that influenced cultural development across the Western Hemisphere. The Mesoamerican observatory tradition represents perhaps the most architecturally integrated ancient astronomical achievement, demonstrating successful combination of advanced mathematical knowledge, precision engineering capabilities, and sophisticated astronomical understanding. These monuments provide compelling evidence for advanced scientific capabilities in pre-Columbian America while preserving astronomical information that continues to challenge conventional archaeological interpretations. The global significance of Mesoamerican astronomical achievements extends beyond regional cultural importance to fundamental questions about ancient scientific capabilities and the widespread development of sophisticated astronomical knowledge among prehistoric human civilizations worldwide. African star temples. Across the African continent, from the ancient temples of Egypt to the stone observatories of southern Africa, archaeological evidence reveals sophisticated astronomical knowledge that encompasses understanding of planetary mechanics, stellar evolution, and cosmic phenomena extending far beyond conventional expectations for ancient civilizations. These African astronomical achievements demonstrate precision and sophistication that rivals modern scientific understanding while preserving knowledge systems that have influenced global astronomical development for millennia. The Nabta Playa stone circle in southern Egypt, dating to approximately 6000 BC, represents perhaps the oldest sophisticated astronomical observatory yet discovered. This prehistoric monument incorporates alignments that demonstrate detailed knowledge of stellar mechanics, planetary movements, and cosmic cycles spanning thousands of years. The circle's megalithic stones mark positions corresponding to calculated stellar positions during various prehistoric epochs, accounting for the precession of Earth's axis across periods of several thousand years. The mathematical precision required to achieve these alignments suggests that Nabta Playa's builders possessed sophisticated astronomical knowledge and calculation capabilities over 8,000 years ago. Recent analysis using advanced computer modeling has revealed that Nabta Playa incorporates alignments with calculated positions of planets invisible to naked eye observation. The monument's stone arrangements mark positions corresponding to Jupiter, Saturn, and outer planetary movements during specific prehistoric periods, suggesting advanced astronomical knowledge predating written history. The stone arrangements at Nabta Playa encode mathematical relationships that correspond to stellar distances and galactic structural features. The spacing between megalithic elements matches stellar parallax measurements for nearby stars, demonstrating understanding of cosmic scale and stellar mechanics that modern astronomy achieved only through advanced technological observation. The temple complex at Dendera in Egypt contains perhaps the most sophisticated astronomical ceiling painting in ancient art. The famous Dendera zodiac incorporates planetary position markers that account for outer solar system bodies and their orbital mechanics with extraordinary precision. The zodiac includes mathematical relationships that encode information about planetary orbital periods, including accurate calculations for the synodic periods of outer planets as observed from Earth. These calculations require knowledge of absolute orbital periods and positional mechanics that should not have been available to ancient astronomers using primitive instruments.